Hello, how's everyone doing? It's been quite some time since my last stream. I think this is my first stream in April. It's been like more than 7 days. Uh, okay, I'm going to be learning C++ again. I finished chapter 16 last time and I'm going to start chapter 17. It seems to be about STD arrays and C style arrays. Uh, wait, hold on. I'm opening my editor, but it's taking so long. Okay, let me just change to full screen. Okay, so I finished chapter 16 last time. I'm going to be starting with chapter 17. It seems to be about STD arrays and C style arrays. Okay, 17.1 Introduction to STD Array. In lesson 16.1, Introduction to Containers and Arrays, we introduced containers and arrays. To summarize, containers provide storage for a collection of unnamed objects called elements. Arrays allocate their elements contiguously in memory and allow fast direct access to any element via subscripting. C++ has three different array types that are commonly used: std vector, std array, and C-style array. In lesson 16.10, std vector resizing and capacity, we mentioned that arrays fall into two categories: fixed size and dynamic arrays that can be resized anytime. Why not use dynamic arrays for everything? Dynamic arrays are powerful and convenient, but like everything in life, they make some trade-off for the benefits they offer. STD vector is slightly less performant than fixed size arrays. In most cases, you probably wouldn't notice the difference. STD vector only supports const expression in very limited contexts. In modern C++, it is really this latter point that's significant. Const expression arrays offer the ability to write code that is more robust and can be optimized more highly by the compiler. Whenever we can use const expression array, we should. If we need a const expression array, std array is the container class we should be using. Std array is defined in the array header. It is designed to work similarly to std vector, and as you will see, there are more similarities than differences between the two. One difference is in how we declare an std array. So vector is like this, and then array int, and then 5. Our std array declaration has two template arguments. The first int is a type template argument defining the type of the array element. The second 5 is the integral non-type template argument defining the array length. The length of a std array must be a constant expression. Okay, because it's fixed size, I'm guessing. Note that non-constant variables and runtime constants cannot be used for the length. So length is a runtime constant. Error length is not a constant expression. Okay. A zero-length std array is a special case class that has no data. As such, calling any member function that accesses the data of a zero-length array will produce undefined behavior. Perhaps surprisingly, std array is an aggregate. This means it has no constructors and instead is initialized using aggregate initialization. As a quick recap, aggregate initialization allows us to directly initialize a member of aggregates. To do this, we provide an initializer list. So we have Fibonacci 0, 1, 2, 3, 0, 1, 1, 2, 3, 5. Copy list initialization using brace list. And then list initialization using brace list. This is preferred. Each of these initialization forms initializes the array members in sequence starting with element 0 or starting with 2 and then 3 and then 5 and so on. If an array is defined without an initializer, the elements will be default initialized. In most cases, this will result in elements being left uninitialized. Because we generally want our elements to be initialized, std array should be value initialized using empty braces when we define with no initializers. So over here, in elements are left uninitialized. Over here, member value initialized. This is preferred. And over here, members value initialized. Or this for vector. If more initializers are provided in an initializer list than the defined array length, the compiler will error. Const and const expression std array. A std array can be const even though the elements of const std array are not explicitly marked as const, they are treated as const. Std array has full support of const expression. This support of constant expression is a key reason to use std array. So class type argument deduction for std array. Using ctad in C++17, we can have the compiler deduce both the element type and array length of a std array from a list of initializers. Oh, I see. So over here, the compiler deduces that it's integer with the length 5. We favor this syntax whenever practical. If your compiler is not C++17 capable, you will need to explicitly provide the type and length template arguments. So over here is an error. Too few template arguments, length missing. The too few arguments, type missing. So we either provide both or none. However, template argument detection used for function template resolution does support partial omission of template arguments. Since C++20, it is possible to omit the array length of an std array by using std2array helper function. I see. Unfortunately, using std2array is more expensive than creating an std array directly because it involves creation of a temporary std array that is then used to copy initialize our desired std array. For this reason, toArray should only be used in cases where the type can be effectively determined from the initializer and should be avoided when an array is created too many times. For example, because there is no way to specify a letter of type short, you could use the following to create an std array of short values. Constant expression auto short. So wait, you can't do like std array short 5. That would give an error. You have to use this. Just like std vector, the most common way to access elements of an array is by using the subscript operator. As a reminder, this operator does not bound check. If an invalid index is provided, undefined behavior will result. What type of initialization does std array use? Our std array is an aggregate, so it uses aggregate initialization. What should you explicit? Why should you explicitly value initialize an array if you are not providing initialization values? A std array will default initialize members if no initializers are provided. This will leave elements of most types uninitialized. Define std array that will hold the high temperature for each day of the year to the nearest tenth of a degree. So double 365. Or each day of the year. So that's why they have an array of 365 days. Initialize an array with the following value: HELLO, print the value of the element with index 1. So HELLO, array 1. So length and indexing. We discussed the unfortunate decision to make the standard library container classes use unsigned value for length and indices. Because std array is a standard library container class, it is subject to the same issues. In this lesson, we will recap ways to index and get the length of std array because std vector and array have similar interfaces. This will parallel what we covered for vector. But since only array has full support of constant expression, we will focus a little more on that. Before proceeding, now would be a good time to refresh your memory on sign conversions or narrowing conversions except when a constant expression. The length of an array has type size t. std array is implemented as a template struct whose declaration looks like this. As you can see, the non-type template parameter representing the array length n has type size t. As you're probably aware by now, size t is a large unsigned integral type. Thus, when we define an array, the length of the non-type template argument must either have type size t or be convertible to a value of type size t. Because this value must be a constant expression, we don't run into sign conversion issues when we use a signed integral value, as a compiler will happily convert a signed integral value to a size t at compile time without being considered a narrowing conversion. Prior to C++23, C++ didn't even have a literal suffix for std size t as an implicit compile time conversion from int to size t. Typically suffices for cases where we need a constant expression size t. The suffix was added primarily for type detection purposes, as constant expression auto x will give you an int rather than a size t. In such cases, being able to differentiate int from unsigned integer. Is this unsigned integer? Without having to use an explicit static cast is useful. The length and indices of std array have type size type, which is always std size t. Just like vector array defines a nested type def member named size type, which is an alias for the type used for the length of the container. In the case of std array, size type is always an alias for std size t. Note that the non-type template parameter defining the length of std array is explicitly defined as size t rather than size type. This is because size type is a member of array and isn't defined at that point. There are three common ways to get the length of array object. First, we can ask array object for its length using size. So array.size. Unlike string and string view, which have both length and a size member function, array only have size. Second, in C++17, we can use the std size non-member function. Okay, Finally, in C++20, we can use std_size non-member function, which returns the length as a large unsigned integral type. I forgot what this meant. Pointer diff underscore t. Because the length of an array is constant expression, each of the above function will return the length of an array as a constant expression value. This means we can use any of these functions in a constant expression, and the length return can be implicitly converted to an int without being a narrow conversion. Array, constant expression, integer, length. So return value is constant expression size t and can be converted to integer, not an arrowing conversion. Due to a language defect, the above functions will return a non-constant value when called on an array function parameter passed by a constant reference. Subscripting array using this operator or the at member function. In the prior lesson 17.1, we covered that the most common way to index an array is to use a subscript operator. No bounds checking is done in this case, and passing in an invalid index will result in undefined behavior. Just like vector array has an at member function that does subscripting with runtime bound checking. We recommend avoiding this function since we typically want to do a bounds check before indexing. And you want compile time bound checking. Both of these functions expect the index to be of type size type. If either of these functions are called with a constant expression value, the compiler will do a constant expression conversion to size t. This isn't considered to be an arrow conversion, so you won't run into sign problems here. However, if either of these functions are called with a non-constant expression signed integral value, the conversion to size t is considered narrowing, and your compiler may emit a warning. We discussed this case further using std vector in lesson 16.3. std get does compile time bound checking for constant expression indices. Since the length of an array is constant expression, if our index is constant expression value, then the compiler should be able to validate at compile time that our constant expression index is within the bounds of an array. However, the subscript operator does not do any bound checking by definition, and the at member function only does runtime bounds check. The function parameter can't be constant expression, so how do we even pass a constant expression index? To get a compile time bounds checking, when we have a constant expression index, we can use get function template, which takes the index as a non-type template argument. So print the value of element with index 3, and this is invalid. This will give compile error. And all of this is happening at compile time, right? Inside the implementation of get, there is a static assert that checks to ensure that the non-type template argument is smaller than the array length. If it isn't, then the static assert will halt the compilation process with a compilation error. Since template arguments must be a constant expression, get can only be called with constant expression indices. Initialize array with the following values, print the length of the array, and then use the 3 operators to print the value of the element at index 1. So I will do include array and then std array. ELLO. So std cout array, we want one array dot add, and then std dot get. This is what they wanted, right? Why is this get not highlighted? Or std get. Wait, how do we use the get function again? Std get. Oh, like that. I don't know why did I do this. Std get one array like that. Now it works. EEE. Uh, Also, it needs to print the length, right? Okay. Std cout array dot size, right? Five and then EEE. Is that what they did here? Yes, that's what they did. Parsing and returning std array. An object of type std array can be passed to a function just like any other object. That means if we pass an array by value, an expensive copy will be made. Therefore, we typically pass std array by reference, which avoids such copies. So we must explicitly specify int 5 here. CTAD reduces the type to std array in 5. CTAD doesn't currently work with function parameters, so we cannot just specify std array here and let the compiler deduce the template arguments. Okay, I think CTAD has to work at compiler time. That's why it doesn't work here, maybe. Using function templates to pass a std array of different element types or length. To write a function that can accept a std array with any kind of element type or any length, we can create a function template that parameterizes both the element type and length of our array, and then C++ will use our function template to instantiate real functions with actual types and length. Since std array is defined like this, we can create a function template that uses the same template parameter declaration. So they're templating pass by reference. So array pass by reference. Would this use function overloading? Is this an example of function overloading? So using template over here, you're calling int 5. Okay. Note that the type of the non-type template parameter for std array should be size t, not int. This is because array is defined as a template class t std size t and struct array. If you use int as the type of the non-type template parameter, the compiler will be unable to match the argument of type std array t std size t. Okay. It is also possible to only template one of the two template parameters. In the following example, we parameterize only the length of the std array, but the element type is explicitly defined as int. Auto non-type template parameters. Having to remember or look up the type of non-type template parameters so that you can use it in a type template parameter declaration of your own function templates is a pain. C++20 we can use auto in the template parameter declaration to have a non-type template parameter deduce its type from the arguments. Yeah, auto n over here. Oh, and then we can use various different values. Static asserting on array length. Consider the following template function, which is similar to the one presented above. While print element 3 works fine in this case, there's potential bug waiting for the unwary programmer in this program. See it? Potential bug. So we have 3 over here. You have array, you have t and n. I guess if we initialize it with an array that has like 0 length or 1 length or 2 length, then array 3 would be out of bounds check. The above program prints the value of the array element with index 3. This is fine as long as the array has a valid element with index 3. So 9, 7, and then this would still work. This leads to undefined behavior. Ideally, we'd like the compiler to warn us when we try to do something like this. One advantage that template parameters have over function parameters is that template parameters are compile time constants. This means we can take advantage of the capabilities that require constant expressions. One solution is to use std-get. Okay, and then this will cause a compile error. An alternative solution is to use static assert to validate a precondition on the array length ourselves. Static assert. Okay. Syntax aside, passing an std array to a function is conceptually simple. Pass it by constant reference. But what if we have a function that needs to return a std array? Things are a little complicated. Unlike vector, array is not move capable, so returning an array by value will make a copy of the array. The elements inside the array will be moved if they are move capable and copied otherwise. We haven't studied move semantics. There are two conventional options here, and which you should pick depends on the circumstances. It is okay to return std array by value when all of the following are true. The array isn't huge, cheap to copy. The code isn't being used in a performance sensitive context. A copy of the std array will be made, but if all the above are true, the performance hit will be minor. Okay. Returning std array via an out parameter. So array. So reference to an array, and whatever changes you want to make, you make it within the array itself. Wouldn't this be called both an in out parameter? In this case, the caller is responsible for passing the std array by a non-const reference. The primary advantage of this method is that no copy of the array is ever made. There are a few downsides. The method of returning data is non-conventional, and it is not easy to tell that a function is modifying the argument. We can only use this method to assign values to the array, not initialize it. Such a function cannot be used to produce temporary objects. std vector is move capable and can be returned by a value without making expensive copies. If you're returning a array by a value, your std array probably isn't a constant expression, and you should consider using std vector instead. Complete the following program. So we have print array and we have print array 2. So let me just copy this. Copy. Paste. And we need to define print array. Print array is a void function which takes in an array, std array, which takes in a reference to an array, a constant reference to an array, also a template like that. Do we have semicolon within the template thing? No, there's no semicolon. So type name t and then std size tn wait, don't we just need to print n? Hold on. And don't we just need to do this? Is there something wrong here? Array unreferenced formal parameter. Um, Would this work? Maybe unused. Okay, let me see. If I do std, I think it would be easier if I just do array.size. Oh no, I have to print the entire array. Okay, I will just do that then. So I forgot how you do the for loop with the for int index 0. I'll just call it I, and then I is less than, I can do n over here, then I plus plus. Std cout std colon c. I don't know why it does this. Hold on. Okay, and then I think it's safe to use subscript, right? Up like that. Cout. Array dot size. Conversion from int to std first for signed unsigned mismatch. I can just do unsigned. Now it works. So how did they do it? Std const auto e. They did it like this. I forgot about this style. An array isn't limited to elements of fundamental types. Rather, the elements of array can be of any object type, including compound types. This means you can create an array of pointers or array of structs or classes. However, initializing an array of structs or classes tends to trip new programmers up, so we are going to spend a lesson explicitly covering this topic. So I have struct house, and then they're defining a house. type house over here. House 0, house 1, house 2. Initializing an array of struct also works just like you would expect, so as long as you are explicit about the element type. Initialization without explicitly specifying the element type for each initializer. In the above example, you will note that each initializer requires us to list the element type. So you might think to try something like this. Houses, 3 houses. Perhaps surprisingly, this doesn't work. Let's explore why. An array is defined as a struct containing a single C-style array member like this. Struct array. So when we try to initialize houses per the above, the compiler interprets the initialization like this. So initializer for houses, initializer for C-style array member with implementation defined name. Then houses, if we go up, so it's number, int, and int. The compiler will interpret 13, 1, and 7 as an initializer for the first member of houses, which is a C-style array with implementation defined name. This will initialize the C-style array element 0 with 13, 1, 7, and the rest of the members will be 0 initialized. Then the compiler will discover we have provided 2 more initialization values and produce a compiler error telling us that we have provided too many initialization values. So struct array, implementation defined name. Wait, if I do this. Well, it says here it's a class. Let's just test this out. So struct house. Maybe unused. Houses. Thirteen, 1, 7. I'll do this 14 and then 15. And then 2, 3 rooms per 3, 3. I'll do 6. There's 7 rooms per story. Cannot deduce template arguments for std array. So 1138. Initializer list is not a valid type for underscore rest. So what if I do as just one of them? std array houses m3. Let's see. Let's see how well this works. Oh, this works. House number 13 has 7 rooms. Wait. Has stories and so how does it initialize the first one? If I just provide 1, it initializes just fine. Thirteen, 1, 7. If I do 5, this works. If I do 1, this works. So the compiler will interpret 1317 as the initializer for the first member of houses, which is a C-style array with implementation defined name. Okay, this makes sense. So we have array type T is implementation defined name size n, which is a C-style array. And the rest of the members will be 0 initialized. Then the compiler will discover we have provided 2 more initialization values and produce a compilation error telling us that we have provided too many initialization values. The correct way to initialize the above is to add an extra set of braces. Before it was like this, now it's like this. Note that the extra set of braces that are required, within those braces we can then initialize each element individually, each inside its own set of braces. This is why you will see std array initializers with an extra set of braces when the element type requires a list of values and we are not explicitly providing the element type as part of the initializer. Hold on. When initializing array with a class, with a struct class or array, and not providing the element type with each initializer, you will need an extra pair of braces so that the compiler will properly interpret what to initialize. This is an artifact of aggregate initialization and other standard library container types. Brace Elysian for aggregates. Given the explanation above, you may be wondering why the above case requires double braces, but all other cases we have seen require single braces. It turns out you can supply double braces for such arrays. Or even for this one, you can supply double braces. However, aggregates and C++ support a concept called brace elision. Is it elision? Like, well, how do you pronounce? I don't know if the read aloud would take a lot of time. It's going to keep on loading. Read aloud selection, which lays out some rules when multiple braces may be omitted. Generally, you can omit braces when initializing array with a scalar single value or when initializing with class types or arrays where the type is explicitly named with each element. Here's one more example when we initialize a std array with student structs. Okay, let's just close this. Student, then we have student, we have students, student 0 Alex and student 1 Joe. I think this one makes more sense. Note that because std array students is a constant expression, our find student by id function must return a constant pointer. Okay, let's see. So if we do, we have houses. If we do house, this works, right? Yes, this works. And then we have 5 of these. The rest will be 0 initialized, I'm guessing. Yeah. Now let's do house 2, 10, 6. Let's see if this works. Yes, it does. Define a struct named item that contains 2 members. Define an array and initialize it with 4 item objects. Use theta to deduce the element type and array size. So theta single braces due to brace elision. Okay. Update your solution to quiz 1 to not explicitly specify the element type for each initializer. So basically, they would use double braces over here. Yep. No, see that must use double braces. Arrays with references via std reference wrapper. In the prior lesson, we mentioned that arrays can have elements of any object type. This includes objects with fundamental types and objects with compound types. However, because references are not objects, you cannot make an array of references. The elements of an array must also be assignable and references cannot be reseated. So this will cause compile error, cannot define array of references. Okay, this is actually a std array int 2, not an array of references. std reference wrapper is a standard library class template that lives in the functional header. It takes the type template argument t, then behaves like a modifiable L-value reference to t. There are a few things worth noting about std reference wrapper. The operator equal will reseat a reference wrapper. Reference wrapper t will implicitly convert to t reference. The get member function can be used to get a t reference. This is useful when we want to update the value of the object being referenced. Here's a simple example. Function for std reference wrapper. Std array std reference wrapper int xyz. So array1.get5, modify the object in array element 1, and then this will print. So y will become 5. Oh, I see. So this way you can use a reference wrapper to store references. When printing array1, so over here, the compiler will realize it can't print std reference wrapper int, so it will implicitly convert to int reference, which it can print. So we don't need to use get here. Prior to C++17, CTAD didn't exist. So all template arguments for a class type needed to be listed explicitly. Thus, to create a reference wrapper int, you could do either of these. Wait, prior to C++17, CTAD didn't exist, so all the template arguments for a class type needed to be listed explicitly. std reference wrapper int reference1, std reference wrapper int x, and then that goes to reference2. Between the long name and having to explicitly list the template arguments, creating many such reference wrappers could be a pain. To make things easier, stdref and cref functions were provided as shortcuts to create reference wrapper and constant reference wrapper. Note that these functions can be used with auto to avoid having to explicitly specify the template arguments. So x, and then we have std reference, and then we have std constant reference. Now that we have CTAD, we can also do this. So std reference wrapper x. Before, what was the issue? Oh, we needed to have a int over here, but we don't need int anymore. I will read this one and then I will take a break and continue with the, like I will close the stream and then continue with C-style arrays after some time. In lesson 16.9, we discussed arrays and enumeration. Now that we have constant expression std array in our toolkit, we are going to continue that discussion. Using static assert to ensure the proper number of array initializers. When initializing a constant expression array using ctad, the compiler will deduce how long the array should be from the number of initializers. So we have 4 values. If less initializers are provided, then there should be the array will be shorter than expected, and indexing it can lead to undefined behavior. Student names, and then when we are accessing Cartman, we are getting an error when we only have 4 values. We can use static assert to check this. std size test scores. This is equal to max students. Using constant expression array for better enumeration for input and output. In lesson 13.5, we covered a few ways to input and output the names of enumerators. To assist in this task, we had helper functions that converted an enumerator to string and vice versa. These functions each had their own set of string literals, and we had to specifically code logic to check each. So switch, case cat, case dog, case pig, case whale, then default. This means that if we were to add a new enumerator, we would have to remember to update these functions. Let's improve these functions a bit. In cases where the value of our enumerators would start at 0 and proceed sequentially, we can use an array to hold the name of each enumerators. This allows us to do 2 things. Index the array using enumerator's value to get the name of that enumerator, use a loop to iterate through all the names, and be able to correlate a name back to the enumerator based on index. Using namespace, string view literals, and then std array color name. We have black string view, red, blue. Make sure we have defined strings for all our colors. Static assert. Okay. Constant expression string view get color name, type color. Also, if it's the 0, we get the 0 element. If it's 1, we get the first element. If it's 2, we get the third element. Artstream operator. We are overloading this and this. So, shirt color blue. Your shirt is, we input shirt over here, and then output operator get color name. Oh, so it prints the string blue, right? Range based for loops and enumeration. Occasionally, we run across situations where it would be useful to iterate through enumerators of an enumeration. While we could do this using a for loop with an integer index, this is likely to require a lot of static casting of the integer index to our enumeration type. Unfortunately, range-based for loops won't allow you to iterate over the enumerators of an enumeration. Wait, hold on, what are they complaining about? So we have this outstream, and then use a for loop to iterate through all of our colors. Unfortunately, range-based for loops won't allow you to iterate over enumerators of an enumeration. Static cast color type I. I don't get what the issue is. Shouldn't we iterate over color name? Color type I. Oh, I mean, we are using this operator, right? We are overloading the OStream, this function over here. And then we are, if we use this operator, then it outputs the name of the color. So instead of 0, it's outputting red or black in this case. It's outputting black. So, so I'm guessing this would cause an error. Range-based for loops won't allow you to iterate over the enumerators of an enumeration. So can't traverse enumeration. What do you call this? This is a normal for loop, and this other one is a range-based for loop, which doesn't work. There are many creative solutions for this. I mean, what we had previously was a solution, I guess. Since we can use a range-based for loop on an array, one of the most straightforward solutions is to create constant expression std array containing each of our enumerators, then iterate over that. In the above example, since the element type of color types is color type, variable c will be deduced as color type, which is exactly what we want. So color types, let's see, color constant expression std array types. And then we can do range based for on a std array. Okay, so we have defined std array over here, types, and then we can do black, right? We can loop through this, but we can't loop through these. Define a namespace named animal. Inside it, define an enum containing the following animals: chicken. Hold on. Namespace animals. Animal, or just animal. And then inside it, define an enum containing the following animal. Okay, so let's call the enum type. Is the convention to use capital letter? Or, yeah. So what were the animals again? Chicken, dog, cat, elephant, duck, snake. And then max animal. Also create a struct named data to store each animal's name, number of legs, and the sound it makes. Struct data to store name, std string, include string. You have name, int number of legs, and then std string sound. Right. And then create std array of data and fill out a data element for each animal. Std array animal underscore data. It's like this. No, I don't think we need this. Std array. Let me think. Do we need semicolon at the end of a namespace? Okay. Data, then max animal. And then we have, I think we need double braces. Let me think. So name is chicken. Number of legs to buck. Chicken, dog, 4, bark, meow. Cat. And then we have elephant. What's the sound of elephant? I don't know the sound the elephant. Duck. Quack. And then snake. Let's see if there are any errors. This needs to be like constant expression. Constant expression. X. Okay, what's the error? Cannot convert argument 1 from int to constant element const. Let's see. So name, number of legs, and then sound. should use string v on all of these. Where is the actual string literal stored? Is it stored in the data segment of the process? And then in order to use string v, I have to do this, right? So what's the issue? The issue is at line 18, 5. Type int unexpected. What do you mean? So name string. I don't understand. Initializing cannot convert from int to std string. Oh, I put semicolon here. Is there an issue with struct? Do you use semicolon for struct? I'm forgetting everything. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. I think you do this over here. I think. I'm not sure. And let me see how they did it. So type and then struct. Yeah, they added a semicolon. I should do string underscore view. Okay, so we have string view integer and then ask the user to enter the name of an animal. If the name does not match the name of one of our animals, tell them so. So stdcin std string user. Should I use underscore? Okay, never mind. Username. Should I use underscore or like I should just use underscore. User name. And then std cout. Input name. For const auto animal data bool animal exist is equal to false if animal data if Wait, how do we do this again? This should work, right? Const types. Why isn't this syntax highlighted? Oh, now it works. So if animal info is equal to username, then animal exist is equal to true. If not animal exist, std is cout. Your animal is not in our database. So let's see. Let's see what's the error. So I did 0, right? Oh, no, wait, not 0. It should be dot name. I should get rid of this and this. Bob, your animal is not in our enum. Now I should type chicken. Right. Now let's see. If the animal exists, what do they want? Otherwise, print the data for that animal. Right. Should do this. I should do break. And then I should also std cout animal dot name has dot numlex lex and sys animal dot sound. So let's see. Duck. Duck has 2 legs and says quack. I should do this. Then print the data for all of the other animals that didn't match their input. What? Enter an animal. Here's the data for the rest of the animals. Okay. So I have to do for loop again. else. So if the animal exists, do the for loop again. Uh, do this. Here is the data for the rest of the animals. std out. Let's see now. I should put this in a function, this for loop thingy. So if I print dog, dog has 4 legs and says park, here is the data for the rest of the animals. I should remove the break statement. So elephant. Elephant has 4 legs and says dude. Here's the data for the rest of the animals. Okay, I guess that's good enough. Or even if they couldn't find the animal, we still need to print. So this should happen regardless. If animal doesn't exist, this should happen regardless whether they found the animal or not. Dog. Dog has 4 legs and says park. Here's the rest of them. Now let's try Bob. Animal is not in our enum. Here is the data for the rest of the animals. Okay. Animal, data, and then types. Then data, static assert. Okay, I will close the stream now, but I think I will take a break and then I'll start doing C style array stuff. Okay, I will end the stream here then. I'm feeling I have like headaches and stuff. I don't know why. Okay, anyways, see you, I don't know when. Bye.